Hello, everyone. My name is Johannes. I'm the CEO, co-founder of Diffraqtion. At Diffraqtion, we see further and we think faster, and we bring the intelligent vision to satellites and machines. So if you ever dropped something and caught it instinctively, that wasn't your brain doing the thinking, it was your eye. Your eye actually is not just a camera, it's a very fine-tuned tool that can, on its own, instinctively react to things, and much faster than the brain, make you react to these things. And we built something based on that intuitive insight, and I'll show you that right here. Oops, so that's supposed to play.
The human eye is a masterpiece of evolution. Vast, intelligent, and brilliantly complex. The retina doesn't just capture images, it quickly reacts to shapes and movement, triggering split-second responses faster than the brain. Diffraction's technology computes light like the retina, achieving 20 times the resolution and 1,000 times the speed of a conventional camera. Delivering the world's sharpest machine vision, superpowering tiny satellites at a fraction of the cost.
So what you saw right there is the world's most powerful camera that can do inference and AI on its own. It's a quantum camera, and actually it's the size of this little camera that you see right here. And what you can do with it is you can see 20 times further than any conventional camera can do. And you can also think 1,000 times faster, which means any information that comes through here, till you know what you're looking at, this happens at 1,000 times the speed of even an NVIDIA GPU together with the best camera you can buy. Now, how does this work? This technology is based on 7 years of research of my co-founder, Professor Saikat Guha from MIT. And it works that we use light that comes to your eye or to the camera directly to process that light, instead of taking a picture and then analyzing it. And while we do this with a photonic processor, we can get the maximum resolution that you can ever get from a camera. And that's what you see here. We did an experiment with NASA, and we were looking at stars. And on the left side, you see what is a diffraction-limited star. So this is something that when you go to the optometrist, the last letter you can read, that is your diffraction limit. Then we replaced it with our camera, and we could see there's another star next to it, actually. So we have a wide variety of applications, but we're squarely focused in space. And we start with building a fleet of these satellites that do Earth observation, looking down, and space observation, keeping our assets safe in space from space debris and also adversary actions. The team is fantastic from MIT and Harvard. We also have a VP of product who founded another space startup that raised over $250 million, and a fantastic set of engineers based in Boston. So far, we have done a DARPA SBIR for $1.5 million. We have raised a $2.5 million seed round. We're working with the Air Force, the Space Force, NASA, and SkyFi, which is our distributor of Earth imaging and space imaging. We're part of 5 accelerators and just won first place at the Best Space Innovation of the Year in the US. So thank you very much, and thank you for bringing our vision to bring Galileo up to space, to reality. Thank you.
Thank you, Johannes. Should we start from Nico now, since you didn't get to ask last time?
Great, thanks. I was just wondering, why are you starting in space, and what is the limitation of the camera? There must be some kind of reason why you picked space as the first application.
Correct, yeah. So the camera was born in space. We developed it with NASA and DARPA over 7 years, and it was built to detect first stars and exoplanets. And this, what you see here, is the most powerful Earth observation satellite that exists today. This is 200 times cheaper than a normal satellite, for example, from Maxar, or that any kind of conventional camera would do. This will cost you about $500,000 versus another satellite that will cost you $100 million to get into space. And that completely disrupts space observation and Earth observation. And this is a dual use because you can put it this way and you can look downwards and you can look upwards to the stars. So that's why the main vertical that we are tapping into is space.
I have a thank you so much. Very, very inspiring. Two-sided question. So, how much do you see that this is really like? What's your business model? How much is like a commercial one versus more like a governmental tool? So, how much the funding you believe would need to come from private sources versus the governmental sources?
Yes. So it's a dual-use technology. The main use cases and where you can extract the most value, as mentioned, is space. And then later, there are some other defense use cases too with it. Later on, there will be much more commercial use cases too, which you saw from industrial automation, robotics, cars, and so on. The initial focus of the company is clearly on the dual-use space, so we'll start with our defense partners. You saw that also working with Space Force, NASA, and DARPA. So that's clearly a lot of investment that needs to come from that side till it becomes really small, cheap, and usable for other applications. Same like semiconductors did back in the 60s and 70s when NASA first piloted them.
I'm very curious, what's been surprisingly hard parts of building Diffraqtion?
Yes. I mean, obviously, we are operating at the limits of quantum mechanics, which means we need to find talent which has the intersection of photonics, optics, AI, and also quantum information theory. So to find people in that setting and to bridge them all together is extremely niche topic. So we had a very broad search for talent to get them all together, but also then later on advisors to sell it first into a very complicated ecosystem of defense, both in the US, but also for our NATO allies. Thank you.
What are the commercial use cases beyond space and defense where you would actually see like this kind of high resolution camera needed?
Yes. So there's about 5.5 billion devices that are called physical AI that will be out by 2030. So this is everything from basically your smartphone to robots to drones and to cars that drive autonomously. All of these require a quick reaction time. And you saw earlier a picture with where we're looking ahead to the next 10 years where it could be used. For those use cases, the camera needs to become much cheaper, and the reality is that we need to extract a vertical to bring down also all the cost of it and become much smarter, because this is a first-in-kind camera that hasn't been developed yet. But we fully expect this to become widely used, and every single device that will be in the physical AI world will at least think about getting such a camera.
All right. Thanks a lot, Johannes.
Thank you so much.